Hello, welcome to this lesson. In this video, we're going to learn about curvilinear motion. So when I say a curvilinear motion, this is the motion of a particle along a curved path. Some examples are the motion of a stone which is thrown at an angle into the air, and also the motion of a car that is taking a turn on the road. These two are some examples of curvilinear motion. So normally, the paths of curvilinear motions are described in three dimensions. Okay, so for this reason, we will use vector analysis to derive the formulas for the particle's position, velocity, and acceleration. So let's look at how you are going to do this. So from this figure that I have here, you have a particle traveling along the curved path S, which is drawn in blue. Okay, and then the particle is indicated with the big red dot. Okay, so what will happen is that if the particle is at a certain point in this 3D space, okay, we can consider the position of this particle at that particular point to be r, okay, which is a vector, and then that will be equal to xi plus yg plus zk. Okay, so we are considering that position of the particle in this figure to be this position vector here. Okay, so what will happen is that the component of this position vector may vary with time as the particle moves. Okay, so what will happen is that this position vector will become a function of time then. So making the component to be, we're going to have the x component to be equal to x of t, and then the y component will be equal to y of t, and then the z component will be equal to z of t, which means that the whole position vector r will become a function of time since the components are changing with time as the particle moves. Okay, so at any instant you may be asked to find the magnitude of the position vector. You can use this expression r equals the square root of x squared plus y squared plus z squared. Okay, so you can use this expression to find the magnitude of the position vector. So to distinguish this from the actual position vector, I'm going to bring the magnitude symbol. So this will be the expression to find the magnitude of the position vector r. Okay, and also we can specify the direction of the position vector using a unit vector. Okay, so that would be the unit vector u r, which will be equal to the actual position vector r over its magnitude. Okay, so when you do this, you are going to get the vector that gives us the specific direction of the position vector. Okay, so from here, when we take the first time derivative of the position vector, we are going to get the velocity of the particle. Okay, so you are going to have the velocity of the particle to be the derivative of the position vector r with respect to time. Okay, so when we do this, we're going to have the xi dt, okay, plus, let me put this in brackets, plus dy I dt. Let me write this again, dy I dt, okay, plus the y should go with d rather, not I. So you're going to have dyg dt, okay, then you're going to have plus dzk dt. Okay, so when you do this, you are going to get the expression for the velocity of the particle. Okay, so what I'll do is that I will further rewrite this as v equals dr dt, okay, which will be equal to dx dt I. Okay, I'm rewriting in this way so that you can see it well. Plus dy dtj plus dz dtk. So this will be the expression for the velocity. Okay, so I can represent dx. Okay, that's I can represent dx dt, okay, with vx, okay, and then dy dt with vy, and then dz dt with vz. Okay, so when I do this, we can write the velocity expression as vxi, okay, vxi plus vyj plus vzk. This is much more simpler than the first expression that you wrote, which is this expression. Okay, so that will be for the velocity. Okay, so sometimes you might not see vx, vy, and vz. Okay, and you'll be seeing something like this x dot. Okay, this is the same as vx. Okay, which is the first time derivative of the position vector. That's the y component of the position vector. Similarly, we're going to see y dot, which is the same as vy, which is the first time derivative of the y component of the position vector. And also you're going to see z dot, which is equal to vz. Okay, they are all the same. So if you don't see vx, vy, vz, and you see x dot, y dot, and then z dot, they are also um and they're also representing the velocity, okay, or the first time derivative of the position vector. You may be asked to find the magnitude of the velocity vector. Okay, so in that case, I'm going to have the magnitude to be equal to the square root of the component. Okay, so that will be, we're going to have vx squared plus vy squared plus vz squared. Okay, so this would be the expression for the magnitude of the velocity vector. So we can specify the direction of the velocity vector with a unit vector uv, okay, which will be equal to the actual velocity vector v divided by its magnitude. Okay, so when you do this, you are going to get the unit vector which will specify the direction of the velocity. Okay, so we are going to do the same thing for the acceleration vector also. So let's look at what will happen. Okay, so for the acceleration vector, okay, you can do it in two different ways. You can choose to differentiate the position vector twice to get the acceleration vector, or just differentiate the velocity vector once with respect to time to get the acceleration vector. Okay, so let's cover what that will be. Okay, so for the acceleration, we're going to have the acceleration to be equal to, first of all, you are differentiating the velocity vector with respect to time. Okay, so that would be dv dt. Okay, so when I do this, we're going to have axi plus ayj plus azk. Okay, this will be when we differentiate the velocity vector with respect to time. Okay, you might also see um something like a equals dv. Okay, let me not use uh Okay, let's do it this way. Okay, let's continue that way. We are going to have the acceleration to be equal to, you will see, x double dot, okay, I plus y double dot, j, okay, plus z double dot k. Okay, we might also see this in some situations. Okay, so to find the magnitude of the acceleration vector, we're going to use the expression square root of ax squared plus ay squared plus az squared. Okay, so when you do this, you're going to get the magnitude of the acceleration vector. Okay, and then you can specify the direction of the acceleration vector using the unit vector ua, which will be equal to the actual acceleration vector a over the magnitude. Okay, so this is what you're going to learn about curvilinear motion in this lesson. Okay, so for us to understand this concept better, we are going to try our hands on this example. So the question says that the position of a particle is represented with the vector r equals 3t cubed I plus t minus 4t squared j, where time t is measured in seconds and position r is measured in meters. A. Determine the displacement of the particle during the time interval t equals 2 seconds and t equals 4 seconds. And then B. Determine the acceleration of the particle at time t equals 3 seconds. So let's look at how we are going to do this. So we have to first of all find the displacement of the particle. Okay, so to do this, you are going to substitute the given time and the given time boundaries, okay, into the position vector expression. Then we find the difference, and then that will give us the displacement. So let's look at that. So we have the position vector r to be equal to 3t cubed I, okay, and then plus t minus 4t squared j. Okay, so first of all, we are going to find the position at time t equals 2 seconds. So we are going to have r sub 2 to be equal to 3 into bracket 2 cube I, okay, plus 2 minus 4 into bracket 2 squared j. Okay, so let's simplify this. So when I do this, I'm going to have r2 to be equal to 3 multiplying 2 cube, that gives us a value of 24. So I'm going to have 24 I. Okay, and then I'm going to do the same for the term in the bracket. So I'm going to have 2 minus 4 multiplying 2 squared, and then that gives us a value of minus 14. So I'm going to have minus 14j. So I'm going to do same thing for the second time value. So I'm going to have 3 into bracket 4 cube I, okay, plus 4 minus 4 into bracket 4 squared multiplying j. So let's simplify these two and see what you get. So 3 multiplying 4 cube will give us a value of 192. So we have 192 I. Okay, and then for the second term, we have 4 minus 4 multiplying 4 squared, and then that gives us a value of minus 60j. So we have minus 60j here. So to find the displacement, we're going to have the displacement to be r4 minus r2. Okay, so let's look at that. So I'm going to have 192 I, okay, minus 60j. And then I'm going to have minus 24 I minus 14j. Okay, so let's do this computation and see what you get. So I'm going to have 192 minus 24. That gives us 168I. Okay, 168i. Let's look at the second term. We're going to have minus 60 minus 14. Then that gives us a value of minus 46j. Okay, so this will be the value for the displacement within the time interval 2 seconds and 4 seconds. So now the next thing is to determine the acceleration of the particle. So let's look at how we are going to do this. Okay, so to determine the acceleration of the particle, you see that you are given the position vector. Okay, so to find the acceleration vector, you have to differentiate the position vector twice, like I said earlier on in the explanation. So we have the position vector r, which is equal to 3t cube, 3t cube I, okay, plus t minus 4t squared j. Okay, so this is what you have. So I'm going to differentiate this with respect to time. Okay, for the first time, that will give us the r dt. Okay, so when you do this, this is actually giving us the velocity. So I'm going to have 3 times 3, which is 9. And then you're going to have 9t squared I. Okay, and then when I differentiate the second term also, when I differentiate t, we're going to have 1. Okay, and then when I differentiate 4t squared, we're going to have minus 8t squared g. Okay, sorry, it's just minus 8t, there's no square there, so I'm going to have minus 8t j. Okay, so this will be for the first derivative. So I'm going to differentiate this again, which will actually give us the acceleration. So I'm going to have the acceleration to be equal to dv dt. Okay, so when you do this, we're going to have the derivative of 9t squared will give us 18t. Okay, and then don't forget the I, and then let's differentiate the second term. When I differentiate 1, I'll get 0. Then when I differentiate 8t, I'll get minus 8, and then the g. So in all, you're going to have the acceleration to be 18ti minus 8g. And being asked to determine the acceleration of the particle at time t equals 3 seconds. So all you have to do is to substitute the 3 seconds into the acceleration expression. So I'm going to have the acceleration at the time 3 seconds to be equal to 18 multiplying 3 I minus 8g. Okay, so this will give us 18 times 3 will be 54. So I'm going to have 54 I minus 8g. So this will be the answer. In case you are asked to find the acceleration and unit vector, sorry, you are asked to find the magnitude and then the direction of the acceleration vector, like we learned earlier on, you can use the formula. As for the magnitude, you can do it as the square root of the 54 squared plus the 8 squared. Okay, and then this will give us the magnitude, and then to find the direction, you can use the unit vector u8 equal to the actual acceleration vector over the magnitude. Okay, and then this will give us a specific direction for the acceleration vector. That's all for this video. Thank you very much for watching. Please make sure you like the video and subscribe to the channel.